This video illustrates the process of building a logistic regression model that generalizes to different geographic locations and accurately predicts the probability that an area will be inundated with floodwater. This product could help communities identify at-risk areas and thereby allot appropriate resources in advance of floodwaters arriving, providing a powerful advantage in the effort to keep people and property safe from rising waters. Using domain knowledge and a top-down strategy in which we began with the outcome, flood, inundation, and Calgary, we attempted to backwards engineer the parameters that help explain flood inundation. We trained the model on features in Calgary and then applied the tool to Montreal.
One benefit to machine learning is that a model mathematically identifies the significance of variables based on the provided data. In other methods, variable significance is arbitrarily assigned, often resulting in variation of results between different analysts. In our model, most of the features proved significant, except distance to major roads and land cover categories, forest and urban. Flow accumulation helps account for the impact of relative shifts in topography. The two cities have very different elevation levels, Montreal being uniformly at a much lower elevation than Calgary. The positive relationship between forest density and inundation could relate to the role of wooded areas as riparian buffers in Calgary. With the understanding that distance and density to a particular feature may describe spatial relationships better than simply feature A, we used a variety of methods to create features. For example, after downloading surface hydrology shapefiles for Montreal and Calgary, we subjected the surface water features to Euclidean distance, then took the mean distance value, which resulted in a fishnet of average distances. The resulting model is able to predict the probability of flood inundation in both Calgary and Montreal. This model and accompanying evaluation differs from other approaches in that many analyses stop at these predictions. However, we've added measurable diagnostics that allow us to assess model performance defined by prediction accuracy and generalizability. There are many metrics that help us do this.
But perhaps of the most interest to planning and policy purposes is the assessment of true positives and true negatives by way of the confusion matrix and ROC curve. While this confusion matrix shows a relatively high value of actual positives predicted as positive, which is good, our specificity and sensitivity values are unbalanced. The model says there will not be flooding, where in fact there was flooding 42% of the time, which is problematic for flood preparedness and decision-making, since it is preferable to be over-prepared rather than under-prepared. Interestingly, many of the areas we failed to predict are next to areas we predicted correctly. This variation may not have an impact at the policy level because of the scale at which policy is implemented. Policy does not consider a grid cell as a unit of implementation.
The ROC curve illustrates the trade-offs in accuracy. The area under the curve is 95%, which suggests that the model may be overfit to Calgary. With increase in Calgary's predictive accuracy, generalizability in other places is reduced. When looking at Montreal, one of the areas that is predicted to flood is around Mount Royal, which local knowledge deems not likely to flood. This could be the result of a natural feature such as tree cover, which in the Calgary data is characteristic of riparian buffers. That feature may be overwhelming the model results when applied to Montreal. In next steps, we would develop the model features in a more sophisticated way in order to improve generalizability.